Hello everyone. We are delighted to present today on the topic of matrices and their wide-ranging applications. This is part of our course on complex variables, integral transforms, and linear algebra. Math 361. I am Habiba Momo, joined by Khairul Alam and Rafia Nujhat Imi. This presentation is conducted under the guidance of Muhammad Jahed, lecturer at the Department of Tripoli, University of Chittagong. Let's begin with a simple yet powerful concept. What is a matrix? A matrix is a rectangular array of numbers arranged in rows and columns, but they are more than just numbers. They are tools to represent and solve complex systems compactly. For instance, the system of equations shown here can be written in matrix form, simplifying the computational process. Matrices aren't limited to textbooks. They are used everywhere, from economics and engineering to weather forecasting and artificial intelligence. Matrices help us model, analyze, and solve real-world problems efficiently. Now we will learn about the applications of matrices in details in linear programming, computer graphics, quantum mechanics, network analysis, circuit analysis, economics, robotics and kinematics, control systems, 3D modeling and animation, structural engineering, signal processing and weather forecasting, control processing, epidemiology, and population modeling. Matrices are at the very core of linear programming, especially when applying the simplex algorithm, a widely used method to solve optimization problems. These problems often involve finding the maximum or minimum value of a linear objective function subject to a set of constraints. Using matrices, we can represent these constraints and objectives in a structured, systematic way. For example, a set of inequalities can be turned into a matrix form, which allows us to solve them using efficient matrix-based operations. What makes matrices powerful in this context is how easily they integrate into computational tools. Software like MATLAB, Excel Solver, and Python libraries such as NumPy and SciPy can perform large-scale calculations in seconds. Let's break down their major advantages. Sensitivity analysis. After solving a linear program, we might want to know how small changes in the input, like changes in resource availability or cost coefficient, affect the solution. Matrices make this analysis fast and clear, solving large-scale problems. In real-life applications like transportation, planning, or resource allocation in industries, linear programming problems become very large. Matrix operations are the only feasible way to solve this efficiently. Representation of constraints. When dealing with dozens or even hundreds of constraints, matrix form is the most practical and scalable way to store and manipulate the data. In essence, matrices transform a complex, real-world optimization task into a clean, solvable computational problem. In computer graphics, matrices are essential tools used to create and manipulate digital images and 3D models. Every visual transformation we see in animation or games like rotating a character, resizing a model, or moving a camera, relies on matrix operations behind the scenes. Some of the key applications include translation. This shifts an object from one location to another in 2D or 3D space. For example, if a character walks forward in a video game, that's a translation applied using matrices. Rotation. Matrices help rotate objects around an axis, whether it's spinning a cube or turning a virtual camera. This operation is done using a specific rotation matrix. Scaling. If we want to make an object larger or smaller, like zooming in or resizing an image, we use a scaling matrix. Beyond object movement, matrices also handle projection, converting 3D coordinates into 2D views so they can be displayed on our screen. They also manage the perspective from the camera, including angle, distance, and depth perception. In image processing, matrices apply filters, like blurring an image for softening effects, sharpening edges for clarity, or adjusting contrast and brightness. So whether we are designing a 3D model in Blender or applying a filter on Instagram, matrices are silently doing the heavy lifting. Matrices offer even more advanced capabilities in computer graphics that are essential for performance and realism. First, combining transformations. In many cases, an object undergoes several transformations. Say, a character is first rotated, then scaled, and finally moved to a new location. Instead of applying each transformation separately, we can combine all of them into a single matrix using matrix multiplication. This saves time and simplifies the rendering pipeline. Next, animation. Objects in games and animations don't stay still. They move, change shape, and interact with environments over time. Matrices are used to control this frame-by-frame transitions, ensuring smooth motion and transitions. Another key area is shading and lighting. To make a digital scene look realistic, we simulate how light behaves. Matrices are used to compute reflections, how light bounces off surfaces, shadows, how objects block light, surface textures like shiny metal or rough stone. All of this happens in real time using matrix operation, especially in graphics engines like Unity or Unreal Engine.
Welcome to the strange world of quantum mechanics, where everything is made of possibilities. In the strange world of quantum physics, particles behave like dreams until you measure them. And to measure them, you need matrices. Quantum states are vectors, where we use matrices to work with vectors and understand how the particle behave. Operators like spin, momentum, and energy are all matrices acting on the state vector. Even the legendary equation, Schrödinger equation, the most popular in mathematics, also a matrix equation. In quantum mechanics, the concepts of measurement and the observable are tightly connected to matrices, especially when dealing with systems described using linear algebra and Hilbert spaces. Likely, an observable is any measurable quantity like position, momentum, and energy in a quantum system. Also mathematically, an observable is represented by a Hermitian matrices. By the way, the roles of the universe written in rows and columns. On the next slide, we can see the matrices in economics. I will be presenting how matrices are used in economics, especially in an important model called the input-output model, developed by economist Wassily Leontief. In economics, especially when we analyzing the structure of a country's production system, often we ask how much should each sector produce to meet final demand and support other industries? To answer this, we use matrices, a powerful mathematical tool to model interdependence between industries. From national budgets to economic models, they track how money and resources move. In networks, whether it's power grids, the internet, or traffic flow, matrices connect the dots. They detect weak points, they map out loops, and finally, they find the shortest and smartest path. The headline of this slide is Matrices in Network Analysis. In electrical and communication network analysis, matrices are essential tools for simplifying and solving complex circuits. These matrices represent different aspects of the network's topology and component relationship. Incidence matrix. The incidence matrix represents the relationship between nodes and branches, components like resistor, capacitor, etc. in a network. Also, incidence matrix is used to apply Kirchhoff current law systematically. In the section of admittance matrix and impedance matrix, this matrix related the voltage and current in a network, where admittance matrix represents the edge with which current flows through elements, while impedance matrix represents the opposition to current flow. Analyzing complex networks. When networks become large and contain multiple source and passive elements like resistor, capacitor, inductors, these matrices help reduce computation. Using matrix operation simplifies solving for voltage and currents. Computer simulation. Network simulator like SPICE rely on this matrix representation. Handle nonpolar and large-scale system, especially in power system and signal networks. In machine learning, matrices are fundamental structures in machine learning. They help organize data, perform complex calculation efficiently, and enable models to learn from various types of inputs like numbers, text, and images. To fast calculation, matrices enable fast and efficient mathematical operation, which are crucial for training machine learning models. Algorithms like linear regression, neural networks, and support vector machines rely heavily on matrix operations such as multiplication, inversion, and transposition. Stored data. In machine learning, datasets are often stored in matrix form. Rows represent samples like individual people, transactions, or items. Column represents feature like age, salary, product type, etc. Example, a dataset with 100 students and 5 features like height, weight, age, grade, gender would be a 100 by 5 matrix. Understand text. Matrices help convert text into a numerical form that models can understand. Transformers use large matrices to represent and process sequence of words with attention mechanism. Work with images. Images are naturally stored as matrices or multi-dimensional arrays. A grayscale image is a two-dimensional matrix where each element is a pixel brightness. Also, a color image is a three-dimensional matrix. Convolutional neural networks use matrix operations like convolution to detect pattern in image.
In robotics, matrices play a big role in helping machines move and understand space. Robots work in a 3D world. They need to move, turn, and reach things. To do this, we use matrices to transform coordinates. That means we can rotate, shift or scale the robot's position in space. There are two main problems in robotics. One, forward kinematics, where we figure out where the robot's hand or tool is based on how the joints are set. And two, inverse kinematics, where we decide how the joints should move to reach a certain point. Matrices helps us solve both problems by calculating the robot's position and direction. This is especially important in robotics arms, which are used in factories, hospitals, and even space missions. Thanks to Matrix, robots can move smoothly and accurately, just like a human arm. Structural engineering matrix helps us figure out how buildings and bridges hold up. They tell us how things bend, where they might break, and how to make them strong and safe. Engineers use a method called the stiffness matrix to calculate how forces move through a structure. In control systems like autopilot in planes or mission in factories, matrices help make systems stable and accurate. They let us control speed, direction, and safety in real time. And when it comes to navigation and GPS, matrices are behind the scenes, helping you find your way. Your phone uses something called a Kalman filter, which combines signals from GPS, sensors, and maps to tell you where you are quickly and correctly, even when you are moving fast. So, what are matrices? They are more than just numbers in a box. They help us organize big, complex problems. They are the tools that power computers, graphics, and machines. They turn 3D images into what you see on a screen. They help smart assistants under your bodies. They can predict the weather, track a rocket, or even help doctors see inside the body. Whether you are solving a business problem, teaching a robot how to move, or exploring outer space, you are using matrices. They are everywhere in science, in technology, in daily life, and that makes them powerful. Thank you all for watching and learning with us. We hope this gave you a clear understanding of how powerful and versatile matrices are across disciplines.